Okay, so welcome back again for the last time, last lecture of last course of this week. This is
okay. So first, two comments on the last time. To begin with, we have plenty of discussion and comments about just the Berkeley's equation. So I'd like to say what people wanted me to say. But for hyperbolic problems like the lower p-time with W1 infinity, but for the parabolic problem I was writing, it's just infinity with lower p-time. So as soon as you have maximum principle, it's globally well closed. And I've given a case where there was maximum principle, so it was very sure about that. Second comment of last time. I actually forgot to say something before theorem, so something that was included part of the assumption. The two things that are quite helpful, I will assume that the system is strictly atomic. That gives particular atomicity, but it's a bit more than that. The other thing I will assume also that the system is non-characteristic. So, I already mentioned I will not discuss characteristics. Any characteristic point at all, but I need to assume it's somewhere.
so characteristic means that
that means that the dx part of the dx is always invertible. So this is what you need to get ellipticity in a 1D problem. Essentially, any operator that is not characteristic is elliptic in 1D. So I'm just assuming this. There's plenty of possibilities, plenty of parts. And here, since I am here, my objective is just piecewise constant. So I just mean that two matrices are invertible. Otherwise, I would just assume that it's nowhere, it's everywhere point was invertible. So maybe I can comment that this is something that is impossible if you have two discontinuities. Because the entropy condition, they force the fact that you should have a characteristic quantity. For this reason, if you want to deal with more general classes of discontinuous solution, you have to take into account characteristic quantity, and we know how to do that. I just don't want to discuss it now. I'm assuming the least is possible. Okay. I think we can relax all of this, but much more technical. Of course, not everything is written down. In this case, the strategy is not of this kind. Put behind the result. Okay. Okay. It's kind of used that now. My unknown is phase and the deformation shape. Right system. We not try the nonlinear system, we just try linearization. Thinking about solving a thing two hard problem. With some boundary condition. Then the guys compare for number. But you should think about this as being like time evolution on upwards, another time evolution in R minus. Then there's this here, like a scalar time evolution. And on top of that, you have some d minus one boundary condition. That's more or less what it's in. There's only one thing for which I take derivative, and it's scalar. Again, it's dimensional. It's more like there is one evolution within here. I could say political, usually. The important message is that this is an initial boundary value problem. Not in the scalar case, but otherwise it's really like you are mixing both. So in particular, okay, something I don't here before is to explicitly include in the remuneration of Thompson. So far, I was not really, because if I knew how to deal with the bond with the initial datum, then I could use UML formula to extend the case where there's a forcing by the UML formula, and that's it. And it's that doesn't quite work for the initial boundary value problem. Mostly because just because of this equation and the fact that the initial data of time cannot be replaced in any short term, because this one has to be like with the example of bar. And this is kind of energy in R. So if you just take a Laplace transform, you will see that the fact that you take by the time derivative something like psi 0 times the jump, and it cannot replace any source current. You can replace only the things that are aligned with U, the jump of U. And the thing before we do linear stability, and we not say linear stability. Then the second thing we do is then we apply it to the equation where the source terms are replaced by some quadratic terms. But as before, I lose regularity when I do the non-linear term, they are just linear, they are looking directly. We need to do something to get back to the regularity. And you do add coincidentally. And here I'm set an invariant, and I explain it to you. Let me give the example. And I have not recalled the minimum. an estimate where you don't really gain decay. You don't really gain decay and you don't get nonlinearity. The estimate is linear. Yeah, estimate something, but something that is homogeneous. There's no gain you will not gain in smallness, you will not gain in decay. What you do gain is in regularity. So you more or less what you're proving that the decay of the large regularity is controlled by simply the L2 decay. So then this means that you can provide this with linear stability. Okay? If you do linear stability with some loss of regularity, you see. And then if you have also this, you say, okay, I think there's no loss of regularity. I'm just closing my VML formula or something like just by combining. So this one gains you in regularity, and the other VML type part gains you in decay and non-linearity. Yes. Precisely. Yes. Yes. You involve the two, and you can conclude with continuity argument. Assuming that you have some bad control, and then you are improving the control, concluding by connectivity. That explains how to improve linear stability and also damping, and how it's related. The only thing I'm really assuming is that I have some spectral gap. Actually, the damping is just coming from the fact that I have spectral gap high frequency. But this is an argument also works and you get adrenal decay and you get some touching in low frequency. Okay, it's only you using the fact that you have a gap at high frequency. And information better on spectral problem. What I mean by spectral quality is that I take la place transparent, I consider overforcing as forcing in my problem, and I will say that some lambda is in the spectrum, but I cannot invert what I get by spectral by taking la place transparent. So it's not quite this, it's not exactly relevant in the classical sense. This is something that you want to be able to invert what you get by spectral problem. By data transform. And you see the places are not the same on both sides. So the capacity. The approach I would use to describe it is a very classical. It's for spatial dynamics. I'd like to explain this a bit. Well, think about the angular equation as ODEs. We discuss the properties of the ODEs. Kind of difficult, very robust, but it's kind of restricted to the analysis of background waves that are essentially 1D. So if a dimensional, planar, or radio, something where okay, you have only variation in one parameter. So radio would be fine, planar too, but they're not a full 2D problem. I thought in that expression instead of the formulation of the property expression, you can write it for you, right? That's so. It's giving you the quantity and some pure imaginary value, then you are on the spectrum. And in the example that you have some solutions that are like models of the equation, they are not in the right space because you cannot put them directly, but you can use some cutoff function to build a family of things that are almost solving the problems. That's why I'm using cutoff function like, to make the exponential in the right space. They are not exactly solving the equation almost. So out of that, it seems that the ODE, so the solution of the ODE, either they decay exponentially or they grow exponentially. Plus, it's the same with minus, and so it's in two cases, you have the usually called exponential method. and the following factorization. So the spirit is that once you have this, you know exactly how to solve the ODE part. And the two equations. There's a numerical to do that, up to fixing it to correctly the boundary condition at zero. So you have some freedom in the boundary condition. Its freedom is coming from the fact that you can, if you forget of the remaining boundary condition part, if anything that is decaying to the right or to the left is fine. You can add it to the then it's not. Side precisely the yes. So the schedule and scaling space. We start like this on R+, then can solve with the value of the gain exponentially. If you are starting like this on R minus at 0, then you're taking 2 minus exponentially. So this is more or less the freedom you have in solving. And okay, you still have the freedom of psi prime. So you're just asking that with the freedom you have, you can solve the remaining equation. So that here, we can say that these are like the two first parts. Solving the two first parts is solving equations. Okay, we're going to exposure that we don't have methods. The conditions you have is the initial level and time back. And then you need to solve the boundary condition. This is the map, the link that the map that is need to solve it. It shouldn't be happening. If you know a bit about spectrum, the discussion is essentially the same as okay, I only say it like you'd like to think about the spectrum as two parts. The one is like constant coefficient, the one is like finite dimension. One about constant coefficients, it's the case where essentially the failure is due to the fact that your operator is not even satisfying the rank nullity theorem. The rank nullity theorem and the kernel should be finite dimensional, the range should be of finite dimension, and the two dimensions should agree. So if you are invertible, of course, that works, 0 and 0. So you are, but if you are, I mean, a strong way to be not invertible is not satisfying. And that's the name, okay, not being freedom of index 0. And that's the same as being freedom of index 0 means that you satisfy the rank nullity theorem. And this means that you are invertible up to finite dimension. So then this means also that you check that if you are really invertible or not, you just have to write some determinant of the finite dimensional object. And the rest of the spectrum will be zeros of this finite dimension. Okay, so this determinant generalizes the characteristic polynomial in finite dimension. So more or less, we are trying to find a way to do the same thing. Like there are, in this phase, you're very far from being invertible. When this holds and the dimension of this space doesn't match D, you're also very far from being invertible. And then, okay, if this works, the dimension match, then you can write the determinant. And then the rest of the spectrum is these are the zeros of the determinant, the zeros of the analytic function, so they are isolated, finite dimension, it's as nice as finite image. So I would not propose to object, but the spirit of what we are doing is something that people don't very general. Yes. We can give the keyword behind that, so the determinant function that you build in the end. Like that. Keywords. Essential difference is the impact of the part and the impact of then the kind of function that we put in the rest is equal to or in this case, maybe can answer questions. It's replacing the characteristic when you it's not all of the spectrum like this. It is a part where you are not occupying the condition and then you can write the term. I already was not correctly the I think the smart picking up of this it should be like a sign and sci fi or sign and lambda sign. I have replaced lambda sign by 5. So just to remove the eigenvalue of 0. By doing this, now my problem is doesn't have the eigenvalue of 0 that was in the essence. It's not fundamental, but it's just get rid of it for free. So I will not need to process anything. Okay, even the fact that I have request type 1 by 5 and then. Another way to say this is that in this case, the fact that 0 is in the spectrum just from the fact that psi is nowhere in the equation. So you can always add a constant to psi. Type 1 is in the equation, but not psi. So okay, the one-dimensional freedom is this. Okay, how do I see this? Yes, and quite a lot. Really announce that in this case I know. So. So just like the part that's going from the part that is between. Part that's going, I should fix its initial value at infinity at being 0. So then I solve backward and I get a bit control. Part that is decaying, I can solve it forward and I have the freedom to add. Yeah, that's also the way to solve the ODE without any. I have precisely no freedom because I have exponential like so either things are growing up or they are decaying. So there's not the freedom of getting something that is outside one. I don't know about it. So the same with minus. Then I still need everything is non-linear except for d0 plus and d0 minus. solve the good part. I should solve that part. Let me just plug the formula x equals 0 in the equation and see what I get. When I do x equals 0 in this case, so this part is going out. This is the thing that I will, this part of my unknown. This part is known. It's an integral between 0 and plus infinity. But this is like the forcing term of the equation. Then I get it looks a bit like a conclusion of maybe no better this kind of thing as stable manifold and stable manifold and so on. Okay, but this is a kind of construction. Okay, so then I say that I need to be able to solve that at any term. That's why I think the interpretation is exactly the interpretation of d lambda. And once I've solved, then I can on this I get the thing that I am missing in the formula. I can put it there. If I do that, I get some formulas. That's why you write the Spanish you can yes, do the extension. You get the main term out of that. Ready. There are terms that are coming directly from the F0 is quite clear. It's kind of the F0 there, just giving something directly here. The F, because it's X minus Y is essentially the one you see here with. And then there are the ones that are coming from the fact that you should take what you have at y, you integrate it to 0, you solve at 0, then you are going putting it back in x. Because of this, you get this kind of shape that is not a convolution, it's like complex y, but not a x one. Okay, I can say boundaries on the boundary function is direct, reflected, and this is part. That's the part of that is this function to be the part of exchanging the position that is kept near the shore. Right, so the should have the same position. Let's do things that are good. The one thing I can say is, how do you do the estimate of something like this? So it's not a convolution, it's then you should have in mind classical thing that if you want to estimate something that is given by again, I'm getting the control by interpolation. I'm saying L1 is need to get from formula infinity and infinity 2. And if I know how to do L1 and 1, infinity by interpolation, you get the control in this. Okay. Of course, compatible with reality, and the visual operator has the same shape of your vertex and work. They get to the key of wrong. Let's say I want to do T is equal to 1 in the formula. Yes, I will do that. Yes, I want to do L1 here. L1 is X, so I should do L1 in X, so it's okay. And then it's in X, in Y, and then I'm using L1 as well. This is the thing that I said. But again, which kind of thing I should try. Mostly I have exponential decay everywhere if I stay far away from the central spectrum and from the part where things are failing. Unfortunately, I cannot always do that. Sometimes you have to go through the central spectrum, and then it's good to use the green kernel, because you cannot do it with resultants. It's meaningless to try to go through the resultant will blow up, you can do nothing. If instead of that you're using green kernels, then you can actually move in part where the operator is not invertible, but you can still get some continuous, some analytic extension of the operators. And why is it too soon? It's actually because sometimes okay, so that depends on how the space and the time are comparable. When the time is much larger than the space, then you should put your contour as much as you can to the left. Because okay, to the left of imaginative, because this is where the time will decay. But this tends to go through the central spectrum, and so the space will grow. So it's fine only if the time is much larger than the space. And when this is the reverse, then you are actually improving the decay in space by putting the contour more to the right. But of course, the time will grow. Then, okay, on complicated cases, we have to find a good way to optimize this placement and do these things and cut in plenty of pieces and so on. Okay, this is not a thing. And also, this problem, I don't need it. I really need it for example, that happens in large frequency. And big for two reasons. One is that this is the only obstacle at the linear level. Whether I will invert the Laplace transform, and the only issue here is that things are not integrable near infinity in high frequency. So I need to understand what is going on. So this is one reason. Second reason is that I need to find a structure that is sufficient to get the high frequency non-linear estimate. I need to find a good structure so that I can do the non-linear estimate. And this is hidden in the high frequency bands. So let's do that. Again, I've used my kind of ODE tool, like spatial dynamics interpretation. So the thing that I want to do is when lambda is large, I want to get some diagonal system. So I will try to diagonalize the system as much as I can. And I begin by using the fact that I assume that my system is strictly hyperbolic. So at beginning order, I can diagonalize with distinct eigenvalues. I do that, and then I try to diagonalize further and see what I get. First, using the functions. It's still denoting the plus and minus. But not really good. Now, it's really people think separate. So let's diagonalize, and then I want to diagonalize further. Okay. So I'm in order and follow the diagonal. But if I can do any argument to saying that PV is already given some diagonal order, try to write the next order by including some near items. Yeah, I'd like to get rid of if you look at the system, it's no, I think I just okay, so there was the lambda part, which is already diagonal, then there's the part of order one, and one to diagonalize the part of order one. And then there will be one over lambda, and I could go on forever with that. It will be enough. If you plug this into the equation, you must just need to explain that. So on the left, it would be like tightening order minus one over lambda cube. On the left, it will give you a lambda cube. And this will form a commutator. With the 2 on one side and minus 2 on the other side. Then we get now. That means twice. I'd like to make this a diagonal and I can take this away diagonal, so I just need to diagonalize this. I have the freedom to choose. I will use that. And then I just need to understand what the commutator with the diagonal matrix because if you see diagonal values, and if you just write it down, but what you at the end you can get rid of anything that is off diagonal. Then you could choose to erase the off diagonal part of this. Right. write down. When you are on the diagonal outside, it's just a Q coefficient that you can choose times something that's non-zero. So you can use it to limit anything more. On the diagonal part of the each you take the thing on its one, and you write it as name. The minus because I want to manipulate things that could be positive. Okay. But essentially what I want to do is take a large lambda limit and write what are the real part extension of these things. When lambda is large but purely imaginary, you get nothing but the mean order. That's why you need to get at the next one. But once you got at the next order, then it's fine. You know the sign of the real part in any direction. You need to provide that lambda is large. The eigenvalues now from n lambda you can get. They expand that. Okay. Now I assume that I have a spectrum that I also know that when one of these guys gets purely imaginary, when lambda is in the spectrum. So the fact that this guy cannot be purely imaginary, we force the fact that one J must be positive. Just because we know what is the sign of this guy when the real part of lambda is large. When the real part of lambda is large, the sign of this is the sign of minus some each. And you know that you cannot change the sign because to change the sign, you need to get pure imaginary and then you are in the spectrum. Okay, I told you that when you are going pure imaginary, these guys should have the same sign as this one. In your part, so that project is maybe a bit more than that. Okay, so you know the size of the spectrum that, you know the size of the influence of that. Zero with the thing I used to denote the spectrum gap. Okay. And you also find I'm using so far only the eigenvalues, but I also find the eigenvectors, an extension for eigenvector, if I just do these things correctly. So I also have some limit for the B lambda that should be vertical. And it's particularly clear if you want to just look at the local weight closeness, then what the limit you should consider is the limit where the real part of lambda that gets large. Because the fact that you have a local closeness means that after some omega positive and things are invertible, and so have invertibility, you should look at it with a large real part. Then if you do that, you get This limit, you get you can find the multiple condition with the local representatives. You get not it's the same as before, essentially you can just looking at the same at the space. And leading order of the matrix was just minus lambda this, and when the real part of lambda is very positive, the space is only this one. If you want to get local awkwardness, you need this to be invertible space. You keep the out of the MC. One for the local representatives and for the favor that come out of the field. That's what I want to say about it. For them, now I can go to the linear stability, then we try to consider that thing. For this, I will just figure for the first storm, and the things are not available, so I need to be careful when we extend any of the kernels I had to the experiment. In precise, the thing is that I need to reach the state where this isn't available. There are two mean variables in the space, can it through X and one in Y, and the other one get one to get the control of the action of the tool. This is fine. Okay, this one I can get integrate and don't have so much. And then I need to do something with the depend on lambda. They are minimum. They are certainly not integral. What I will do is just I'm able to identify them. But they are the fact that I cannot do that is the same as I. The fact that they don't give a smooth contribution. So the spectral problem is negative. But the evolution problem is only harmonic. There's no smoothing effect. So we think that in the green kernels of the time evolution, there are things that are not smooth. For the spectral problem, everything is smooth. Okay, so the non-smoothing, the loss of regularity comes from the integral. Something is not integrable, and you get an object that is in the end not smooth. So you get an example of identification. Taking the linear path, solving X, the equation. And a linear path, yes. And it's not decaying on the large, on the imagine part of the it's simply something that's right. The question is now, I'd like to invert the Laplace transform. But you can, I mean, okay, you can just recognize these things that it's, so if you prefer, if you want to invert the Fourier transform. This is like a trigonometric monomial, so if you invert Fourier, it should be a direct mass. Actually, in time, okay, for the transform in time, the thing I'm getting is a direct mass in time. It's not so convenient for the analysis. I prefer to think about this thing as being a distribution in space. Yeah, it's like, okay, I have something that is continuous on the space variable with value in distribution in time. But because of the problem is non-characteristic, I can reverse things. Okay, I can think that this is like the time evolution with values in distribution in space. That's a small exercise to check that this is the same. You have to be careful about the change of value. If you want to check that, I think the easiest way is just to test it against something that is a function of time, like the function of space, and see what it is. And the span of these things are dense in all functions. So, okay, you want to know for this, it's fine. So this is the kind of linear part. If you look at the 1 over lambda, they give you instead of direct mass, a satisfied type functions. Everything is fine. Okay, it acts nicely and everything. It doesn't fit the frame I've shown you before because it's not regular enough. It's not L1, but of course, this is control of the direct mass. And you act with a direct mass or someone who buys this kind of things, you will just have the same function as before. With some exponential in time decay. I'm not saying more about this. I'd like to talk about estimates. And it's not so much that it's the nonlinear we don't care so much. So the thing is that if you get it by energy estimates, then you will probably be able to extend it to nonlinear. So I'd like to get the high frequency exponential decay by an energy estimate. That's the goal. So the art of the strategy is really linear. You would write the integration project of the sign, and that's the same as before on J, I would say. Instead of using a metric P and using project laws, but these are one for one. I was going to say that if you do the energy estimate, I need to be a situation where I do the integration by parts. It's a thing that I can use any thing that is. So I need to choose the correct L to product to estimate. So that's the same as shooting for a piece on this. That's why I don't put it. This one works in the sense that when I apply sigma to A, and A becomes sigma. Yeah. I have some freedom with kind of start on that for everything, but if I revert to the here, then I have to give me a shape such that the integration by part will be very strictly the zero order, but if I use this kind of things, I will just see the zero order. Maybe this is too much notation. That's just a way to check that when you are strictly at coverage, you are symmetrical. And for the energy estimate, it's better to symmetrize. When you have some freedom, and I will use let's try to do estimates. And only H1. I need to go H2 because I need to control W1 in the that's okay. That's but first I estimate this. But then I will count. So that I constant coefficient. That forward will be forward is stronger. That's fine. It means that I can do an integration by part to make the interior part disappear. And when I do integration by part, encore. But I forget about that when you read the discuss it. It's very first to explain how to do the interior part. Then we discuss the problem. So it's still not good. Because nothing is negative. I know nothing about this guy. This is not what is good for them. And what I get is something on the type of problem. I should find a way to do that. Well, we use that's we make up the okay, the expression we give the name of the you want to for hyperflexibility. That's the one that we call it. I think that it is well known in the academic community. It is someone, for one reason that I don't fully understand. It's not so well known in the clinical community, but not too much. Okay. Okay. If we not develop a full because we want to get. So I will like to form a new dxv square in the equation. Because I'd like to form some kind of dissipative negative term of dxv square. So the question I'm asking is, where is dxv? And the answer is it is in the equation. The equation, you see there is dxv somewhere. So if I do a scalar product direct of the equation with dxv, I will get the dxv square in the equation. And this is it is related to the term dxv. And then the question is dxv the time derivative of something? In a way, almost. That's the time derivative of dxv. So this is a lower order term that you can add, and you can create a term that is as dissipative as the higher order term. You write this. Not much more precise, but precise then. Okay. Here, then I will replace a start like input term, and I will reconfigure to what we need to choose. So let's do that. I will choose the term like this. Here, I will choose this guy to get exactly the time. One can work that particularly with your computation of only computation of here we need exactly one. Okay, so I explain I simply with only one commutator because I only need one commutator in here now. Do the computation of no, because I only no. And I can consider. And the fact that I'm doing actual considering is the same as the fact that I was doing large lambda synthetics. Okay, so the fact that I don't care about lower order term is really the same as the fact that I was not caring about one order lambda. Okay, that's the same kind of game and see it's another case. It's something the same but different. If you just see main term. Okay, that's and it's just coming from okay, so the secondary the one that here we find also you d plus this side, then you get 2 d plus dx. Then on the other side, if it's here, you get a dt dx squared. Then okay, you first go from the other side, and the integration by part will create a -1. That's how you get the commutator. And then okay. So again, this is the commutator of the Q with something like this diagonal with distinct eigenvalues. And we have done implementation, so it will be exactly the same thing as before. Because what we need to do is we combine this with the thing I already have here. Okay. Then, That's the one that's negative. So I create the effect of this taking a new way. And by something you control, I've made the color. Yes. Right. Something that like H1. But then I'm adding a strong multiple of L2 to make it pretty like sorry. Let's do it more. Okay. But I want it for H1. Okay, but if I write if I try to solve this with a exponential, I get a sample on this. So I get it with a no. The only thing at some point that we need is to convert our problem that figure out. But discussing that. Before that, let me explain how I do like I need to extend people non-linear equation. H. Then I discuss further. It's only one thing, the diagonalization, because I need the symmetrization to be well done. The rest, I do it up to lower order term, so I don't care. So I just need to work. Oh, I'm going to base yeah, yeah. The diagonalization, the higher part, well, place where you cannot lose regularity, you have to be careful. The non-linear, the other part, you know. Of course, you would be able to do H1. Now it depends on time and space only, because we need to get some Nietzsche component to close the argument. At the H1 level, the estimate doesn't close, you have to do H2, but you don't do the same thing for H2. H2 in H2. There's really nothing to this. Longer. Let me use the toy manipulation. Là, on va l'entendre d'avoir fait follow à l'heure. Donc, ensemble, de ligne en bas. On peut avec this. Including the entry tunnel. Afterwards. Et la famille. Et donc, perdre 0 coordonnée. That's also we do it for higher order derivatives here. Then the question is what to do with that depends on the sign of function. There are two DJs in that DJ.
And some of your the DJs are going.
So in this case, we want to DJ. But the reverse on the other side, DJ negative is good. Then you have to think about what do I do in the third one? That one. I'm followed by the boundary. If I look at one equilibrium condition, it's an equation that relates to the bad terms to the good terms. You're thinking that the good terms, you consider them as sorting terms. And then the bad ones, you will get them by inverting. This is possible by the Kreisler-Kwatlinski condition, but you can do that. And so then you return this, the bad ones, down what the good ones. Okay. And then at this stage, you need to use the freedom I was mentioning at the beginning, but you can, you're allowed to act with some diagonal thing on top of the diagonalization. You can choose the eta k, put large numbers in front of the good one, so that in the end, you create something dissipative. Okay? Like the very good one, you have a huge number, and you know in advance what is the size you need to beat to control the bad one by the good one. Okay, so when you just close by and you just move to the base. I think that was something pretty meaningful. Something that takes into account when you need to that for the compression to that. are the ones creating the booster boundary vector. This one are controlled by some each function like the other ones, and so it's large enough. Okay. Because something I'm not saying that the one thing you're going to automation is not written for derivative. It's written for values. You need also to know how to go from that to the boundary condition for derivatives. But it's the only, I mean, okay, the easy way to do this, since it's in the boundary condition, you cannot really take derivative in space. It's not convenient. But you can differentiate in time. So this is fine. This is inequality for any time. So you can take a derivative in time. Use the equation for basic time derivative by space derivative. And here I'm also using the fact that the condition is non-characteristic. Then I can do this game of replacing dt by dx the way I want. I will not say more about this. I will take the last 5 minutes to just state vanishing viscosity uniform asymptotic result. Beginning with that, I mean, that's that anti-distribution previous year. With this kind of case, I think we made this one. This is then we may keep this. I want to say that because we made this one, like the equation, and we turn on some kind of power down, and then we get something. You get another like this. Okay, yeah, I'll say. It's the being of the data, that's very good. Probably no way. I don't think to be able to show that go to if I say the variable with the way I'm getting a new here. With the problem going this guy, if I want to make it to the extension and do the thing like this. With the on. Uniform mu. What is it? Yeah, what is it? Yes, the equation. But it's something that's not. It's not the main point. The main point is that the technique to resolve. Yes. In time, get to control. Problem and determine what is the song that is a new minus one. So this is so in the uniformity there are essentially two constraints. One is that all the coefficients should not depend on mu. That's why I mentioned the epsilon and the C and the omega everything is not depending on mu. But there is something that is dependent on mu, which is not. So for this to be real, some kind of uniformity, this norm should be essentially like the W1 infinity norm. So it is like the W1 infinity norm if you are far away from the layer. Far away from the layer is equivalent to the. But I need to take into account that there is a shock layer. Okay? The profile itself, its derivative is going like 1 over mu near the location. So you need to do the norm that is adapted to that. So this is something, in fact, that I'm using this is something better from what I found for the initial data that works for the controlling time. It's Making two norm place. Okay, only the denominators are going. But they are going only like okay. They can be large, but only as large as 1 over mu and only on something near the shot. I will not say much about the course of this thing. At this stage, let me just say two things. In my opinion, the two hardest parts are like you need to design the phase in a very careful way that is completely unusual and something far away from what I've seen before. And then you also need, if you want uniformity, you need to close the non-regularity estimate without using energy estimate at any stage. Never, because then you will do some. Okay, so then you have to do something that is much more clever, and you design a very well adapted norm to close the estimate. Okay, I'll stop here.
Thanks, Miss, for the final part of your course. It's really interesting. So, questions?
This should be one and one statement. I think the reading of the show is quite
Yeah.
This question.
What is the question?
From the top.
From the
Top of the left.
yes. Okay. No, it's the G will disappear at the limit. In the limiting profile, there's no G. You just scale by mu, when you put the form. Yes, that's we put 1 over mu, 1 over mu square. There will be a 1 over mu left factor. So there will be in the profile equation when you go to slow thing, there will be a mu in front of the G. So the limiting profile is the one where you have no G. And the U0 is starting with no G. No. Yeah, I think it's like this. So in particular, we are doing the construction by perturbing the disc shock layer corresponding to no source term. Which existence is exactly equivalent to the entropy condition. But the entropy condition for a function like this is exactly the fact that you can connect the two states by the limiting profile. Then you perturb with the source term. And essentially, the stability proof is a bit like this too. We go to this to kind of scale variable so that everything is very smooth. But then plenty of things are very large size at the beginning, and also the gap is outside epsilon. So, yeah.
So I have a more stupid question actually. It's how this compares with say stability results of this kind of the Japanese people, let's say. For example, when they had a shock, basically they were just regularizing the shock and then they were doing some energy estimates around it, right?
Okay, so
but basically, let's say what you were.
And so I should say that if I give up uniformity, then it's very easy. So it has been done like forever. And even if I drop the G part, that is giving you some kind of dissipation, I could use some exponential way to restore this. And this is exactly the mostly these are the Matsumura.
Yes.
Okay. So where you use weight for some kind of dissipation, or you take anti-derivatives, and then there are plenty of things by energy estimate that you can do. But it is really not fitting you at all any kind of uniformity. Okay, and yeah. Okay. Okay, we are in a situation that's always a bit you cannot use neither the regularization in the strong way nor adapt the hyperbolic techniques. That's none of them is wrong. In particular, if you instead of doing that, you do a standard thing where you if you non-uniformity just projecting out the zero mode, putting it in the phase. This is not enough, not at all. The phase will not give you some uniform. You have to choose a very careful phase if you want it to be. It's coming from the fact that you have zero, but you should get it. That is the projection, but the rest of the spectrum is also LC enclosed. So you have to remove part of this too, but it's part of this also in the phase. Okay.
Any other questions? Well, okay, if not, okay, thank Luis again for the